the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
All right. So now we go into section 3.2. I'm not recording this on Zoom, by the way, mainly because they're taking about 3 days to get back your videos that you record, and I want you to get this sooner than that. So I'm using my own software for this, which is kind of nicer anyway. It's not for streaming, but for actual mastering. So here we go. The domain and range of a function, really. Finding the domain of a function defined by an equation. That's a subsection we're in. And this should be old news for you, or old hat for you, if you will. But there is a how-to here. So if you're given a function, as an equation that is, and you're asked to find the domain, the very first thing you're going to do is identify the input values for the function itself. And that is obviously the domain. Identify any restrictions on those, which are restrictions on the domain, and then write the domain in interval notation. You have done this since learning functions, but I'm going to go ahead and take some examples that might be slightly higher level than maybe you've seen in the past. Maybe it'll be the same level. I don't know. But let's go ahead and start with this one right here. State the domain of this function using interval notation. So the very first thing you're going to do is look at the statements within this and look for issues that you would normally find as far as domains are concerned with a function. So as an example here, you know there's an issue with dividing by 0. Normally, I'm not saying you know the exact value for this. What I'm saying is you know that fractions have the possibility to have division by 0, and you have to watch out for that. So that's the only thing that's going to restrict our domain. So let's go ahead and find out what causes division by 0 here. I'll go ahead and erase this. And let's go ahead and factor, because that's really what you're going to do with any type of function. You're going to be basically say, well, I need 64k to the 6th minus 729. I need that to not be 0. Or along the same lines, you could actually decide, you know what, I'm going to set this equal to 0 and find out what causes that. So you could do that either way. I don't care. You can see right here, this might be a difference of squares, or it might be a difference of cubes. It actually could be both. So when you're faced with this type of situation, you might want to test it out. A difference of squares is actually easier to work with. So I'm going to see if this is a difference of squares. Notice I still keep writing that can't be 0, right? So I know 64 is the same thing as 8 squared. I know that k to the 6th is the same thing as k cubed being squared. Now 729, you might not know what that is. But in fact, I would probably say you don't know what that is. But if you just grab a calculator very quickly and take the square root, you'll find out that it's 27 squared. So that's a difference of squares. We have this first item, this last item. So we'll go ahead and use the difference of squares formula. I've written it off to the side here so that it's a little bit easier for you to remember. Playing the role of first would be this 8k cubed. Playing the role of last would be the 27. So factoring here, you'll get 8k cubed minus 27 times 8k cubed plus 27. Again, you don't want that to be 0 because you'd have division by 0 if that were the case. I also want to include the fact that I am using factoring here. So I'm trying to keep good on my word about telling what these implications are for. Those are actually a sum and a difference of cubes. And I've written the sum and difference of cubes formula, factorization formula, off to the right-hand side. And you can see that everything's kind of set up cleanly for us. In fact, maybe I should go ahead and write out what these are really quickly so that you can actually see what's playing the role of first and last in each of those factors. So there you have it. Now we're going to go ahead and use the factorization formula off to the right. And that is memorizable. You should not need a sheet for that or something like that. You should just keep that in your brain as long as you're taking mathematics. So let's go ahead and factor those down. Now I want to pause for a moment before I continue this out. Remember, it is first minus last, and then first item squared, and it's the opposite sign, so plus first times last plus last squared. generally when I'm doing this, I actually focus on these items as first and last. There we go. So first and last. And so if you square the first thing, you get 4k squared. Square the last thing, you get 9. And if you take the product of the first and last, 2k times 3 is 6k. And that's how I got the middle. Now going ahead, we're going to zoom back out here. I'm also going to erase that note down there. And I'll finish out the factoring. Now that's a pretty hefty amount of factoring. And something that I mentioned in class is that those trinomials, I'll highlight them right here, these are going to be prime. So they are not factorable. As long as, I should mention, as long as you've already factored out the greatest common factor, the GCF, those will be prime. There's nothing else you can do with those. And in fact, because they're prime, that means that they'll never become 0. You could check me on that if you want to. You could try to solve 4k squared plus 6k plus 9 is equal to 0. But the problem here is that if you go to solve that quadratic, as I've mentioned in class, you'll want to solve this using the discriminant first. So setting up the discriminant, that's b squared minus 4ac. And b squared here is 36. Minus 4 times a and c is 36 as a product. And that will be negative. That means you have a negative underneath a radical, and that's not worth it. So there you go. That is not ever going to be 0, and actually nor will the other one that's highlighted, the other trinomial. Now it's a good idea to remember what this all was born of. This was the denominator of that rational function right there. And we did all this factoring because we wanted to know what would turn this into 0, or better yet, we wanted to state that that denominator could not be 0. Well, it's the same thing as saying, let's set it equal to 0. So like I said, you could have done all of this with equal 0. I'm just specifically saying, as I go through this, just remember, we're doing this because the denominator cannot be 0. And if neither of those trinomials can ever be 0, then it's only these two pieces right here that we have to be concerned with. So 2k minus 3, that's not allowed to be 0. And 2k plus 3 is also not allowed to be 0. And this will imply that k cannot equal 3/2, and that k can also not equal a negative 3/2. So again, state the domain of the function. Well, the domain, we can plug any other value of k in here to this function, because everywhere else, we're not going to be dividing by 0. So I want to write out the interval negative infinity all the way up to infinity, except I don't want to include these 2 points right here. On a number line, you can see this as follows. I have big old open holes that I have to not include, one at negative 3/2 and one at positive 3/2. Otherwise, I can go ahead and take an k value from anywhere else on this number line. Writing that in interval notation is going to require a union of intervals. The first interval, remember interval notation goes from low to high, so you start from negative infinity and climb all the way up to negative 3/2. However, you cannot include that, so you're going to put a parenthesis there. That is this interval right there. Then you go to the next interval and you glue on to that next interval. Gluing that on means union, and you're going to go from a negative 3/2 all the way up to a positive 3/2. And again, glue on to that yet another interval, starting at 3/2 and going to infinity. And that is the domain of our original function. All values of k in that interval. And so I've noticed this online, some of the homework problems that other people code, they say this, k is an element of, remember that means an element of or belongs to or is in. You don't actually have to write that. That's usually just included in the problem. So you'll see like in the answer box there, right before it'll say like, oh, k is in, and then you have to write the interval. Not a big deal. So there's our first example of stating the domain of a function. So this one looks like yet another rational function, but it's a little bit more complicated. And actually, it's kind of interesting because I did an example like this, a little bit more complicated, for my pre-calculus students just tonight. So let's talk about this. I have a function. I need to figure out what's going to cause issues. Right? I see this is actually a combination of a lot of functions. It's got a square root function right here. And we know that within a square root, you cannot have a negative number. As another square root function downstairs, again, can't have a negative number in there, but also because it's in a denominator, it can't be 0 as well. So let's go ahead and talk about each of those pieces separately. I'll use different colors for this. So for the numerator, we know that 2 minus x must be greater than or possibly equal to 0. Notice how I'm doing it this time. In the previous problem, I was stating what x could not be, but I told you at that time, you could also have stated what x could be, right? So that's what I'm saying here, is that I'm just saying, well, 2 minus x has to be greater than or equal to 0, because it's underneath the radical. So that's another way you could do domain problems. And of course, just by adding x to both sides of this inequality, we get that 2 must be greater than or equal to x. On a number line, I could plot the point 2, and this tells me that x has to be less than or equal to that. So I'm just going to go ahead and put a little bracket there, and I'll highlight everything less than or equal to 2. I know that's not a great highlighting there, but it'll work. All of those x values satisfy or are allowable for the numerator. Now let's step down to the denominator. The denominator is slightly different. Only because, well, if you said that x plus 3 had to be greater than or equal to 0, you're partially correct. It can't actually be 0 though, because it's in a denominator. So I have to take away the equality there, but that's the only thing I have to really fiddle with. Subtracting 3 from both sides of that inequality, we get that x must therefore be greater than a negative 3. I'll draw that on a number line. I'll also try to align that numerically with where it should be on the number line above. Remember, x has to be strictly greater than that, so let me put a little parenthesis there. Some people use open circles and solid dots, that's fine as well. I just like this notation because it's going to tell me the answer. So all the x values that I'm highlighting right here are allowable for the denominator, but the domain of this function is going to be the intersection of those two highlighted regions. If I were to grab a number from way over here, let's say this number over here is 5, while it would be allowable in the denominator, 5 plus 3 is 8, I could take the square root of 8, you cannot plug it into the numerator because 2 minus 5 is negative, and you can't take that square root. It just wouldn't present a real number. So I can tell you right now that anything above 2 is not going to work. Anything below negative 3 is also not going to work. So the intersection of these two domains is going to be the actual domain of this function. I tried to highlight it there, but it didn't really work out well. So let's go ahead and just write it down. So the domain is going to start at negative 3, but not including negative 3, and it's going to climb all the way up to 2, and it can actually become 2. So that's the intersection of those two intervals. And that's it for finding domains of functions for right now. In the next video, we'll step forward into the next topic, which is a subtopic of this, which is finding domains and ranges from graphs.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.